Welcome to Cambridge IGCSE Physics, Lesson 54.1, Spontaneous and Random Emission. Today we explore the fundamental nature of radioactive decay, examining how unstable atomic nuclei emit radiation without external influence. This lesson covers core content essential for understanding nuclear physics principles. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe emission of radiation as spontaneous, meaning it occurs naturally without external triggers. Second, describe emission as random in direction, with particles traveling in unpredictable paths. Third, understand unpredictable decay timing, where we cannot predict when individual nuclei will decay. These objectives align with Cambridge IGCSE assessment, focus on core knowledge and understanding of nuclear physics principles. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, spontaneous emission means natural radiation emission from unstable nuclei without any external cause or trigger. The nucleus decays by itself. Second, random means there is no predictable pattern or preferred direction for radiation emission. Particles travel in all directions equally. Third, unpredictable means we cannot determine the exact timing when individual nuclei will decay. Understanding these terms precisely is crucial for nuclear physics comprehension. Let's explore spontaneous emission, our first core concept. The fundamental principle states that unstable nuclei emit radiation naturally without any external influence. This means radioactive decay happens by itself. The definition is, radioactive decay occurs without external influence or energy input from outside sources. Key features include, first, no external trigger is required. The nucleus decays on its own. Second, this occurs in all radioactive materials universally. Third, the process cannot be stopped or controlled by external means. The diagram illustrates an unstable nucleus spontaneously emitting alpha particles, beta particles, and gamma rays in different directions. Notice how no external force causes this emission. It happens naturally due to nuclear instability. Now we examine random direction of emission. The principle states that radiation is emitted in all directions equally from the source nucleus. The characteristics are, first, no preferred direction exists. Particles don't favor any particular path. Second, there is equal probability in all directions around the nucleus. Third, we cannot predict the exact path any individual particle will take. Fourth, the emission follows statistical patterns only when we observe many particles. Evidence comes from Geiger counter experiments, which detect radiation from all angles around a source. The diagram shows a nucleus at the center with arrows representing possible emission directions. Notice how detectors placed at different positions all register radiation, proving the random directional nature. Our third core concept is unpredictable decay timing. The key principle states that individual decay events cannot be predicted with certainty. Important points include, first, we cannot predict when any specific nucleus will decay. It's completely random. Second, half-life applies only to large populations of nuclei, not individuals. Third, each nucleus has a constant probability of decay per unit time. Fourth, the exact timing is completely random for each nucleus. Half-life is defined as the time required for half the nuclei in a sample to decay. The graph shows the statistical pattern. While we can predict population behavior, individual nucleus timing remains unpredictable. Notice the exponential decay curve with half-life markers showing the predictable population trend despite individual randomness. Let's work through our first example. The problem states, a radioactive source contains 1,000 nuclei. After one half-life period, how many nuclei remain undecayed? We are given initial nuclei equals 1,000 and time equals one half-life period. We need to find the number of undecayed nuclei remaining. Step 1. Apply the half-life definition. By definition, half the nuclei decay during one half-life period. Step 2. Calculate the remaining nuclei. 1,000 divided by 2 equals 500 nuclei. Step 3. Check our answer. 500 nuclei decayed. 500 remain. This totals 1,000, confirming our calculation. Step 4. State the answer. 500 nuclei remain undecayed after one half-life. Remember, while we can predict population behavior, individual nucleus timing remains completely unpredictable. Example 2 examines why radiation detection varies randomly. The problem asks us to explain why radiation detection shows random variation in count rates. Our analysis reveals four key factors. First, emission is spontaneous and random. Nuclei decay without external triggers at unpredictable times. Second, direction cannot be predicted. Particles travel in random directions, not all towards the detector. Third, timing is unpredictable. Decay events don't occur at regular intervals. Fourth, the detector receives variable counts due to these random factors. The conclusion is that the random nature of radioactive decay causes count variation. The graph shows typical count rate data over time, displaying the characteristic random fluctuation. Notice how counts vary unpredictably between 6 and 15 per second, demonstrating the fundamental randomness of radioactive decay processes. Now practice what you've learned with these three questions. Question 1 is basic level. It asks, state three characteristics of spontaneous emission. Think about what makes emission spontaneous and natural. Question 2 is intermediate level. It states, explain why we cannot predict individual decay events. This requires you to apply the concepts of randomness and unpredictability we've learned. Question 3 is advanced level. The question is, a sample has 800 nuclei. After 2 half-lives, calculate the remaining nuclei. This tests your mathematical application skills. For all questions, remember to show you're working clearly, include units where appropriate, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how today's concepts apply in practice. In medicine, radiotherapy uses controlled radioactive sources to treat cancer, relying on the spontaneous emission we studied. The random direction helps distribute radiation effectively. In archaeological dating, carbon-14 dating uses the randomness of decay to determine ages of ancient materials. The statistical nature allows accurate age calculations. In energy production, nuclear power plants rely on controlled nuclear decay principles, harnessing the energy from spontaneous emission. These applications show why understanding randomness and spontaneity matters. Career-wise, nuclear physics knowledge leads to medical physics for cancer treatment, energy sector work in power generation, and research in fundamental physics. Understanding randomness also improves radiation protection protocols, keeping workers and patients safe. Let's review the solutions. For question 1, the answer includes three characteristics. First, no external trigger is needed. Decay happens naturally. Second, occurs naturally in unstable nuclei without outside influence. Third, cannot be stopped or controlled by external means. For question 2, individual decay is random because each nucleus has a constant probability of decay per unit time, but the exact timing remains unpredictable. We can only predict statistical behavior of large populations. For question 3, we calculate step by step. After the first half-life, 800 divided by 2 equals 400 nuclei. After the second half-life, 400 divided by 2 equals 200 nuclei remaining. Now exam success tips. Use command words correctly. State means list facts briefly. Explain means give reasons with scientific detail. Always distinguish between individual nucleus behavior, which is unpredictable, and population behavior, which follows statistical patterns. Remember that spontaneous means no external cause is required. Show all half-life calculations step by step for full marks. Let's summarize today's lesson. The key points to remember are, first, spontaneous emission means radiation occurs naturally without any external triggers or energy input. Unstable nuclei decay by themselves due to internal instability. Second, random direction means emitted particles travel in unpredictable directions with equal probability in all directions around the source. No preferred path exists. Third, unpredictable timing means we cannot determine when individual nuclei will decay, though we can predict statistical behavior of large populations using half-life. These three concepts form the foundation for understanding radioactive decay. For further study, review the characteristics of decay and key definitions regularly. Practice half-life calculations to build mathematical confidence. The next lesson covers types of radiation, alpha, beta, and gamma, which builds on today's work by examining the specific particles and energy emitted during spontaneous decay. Ensure you understand randomness and spontaneity before moving forward.